Yeah. Well, Ash gets film. Yeah. Oh, the legendary? Yeah, that was different.
I'm good whenever.
You good?
Yeah.
Okay. I'll just wait till it's actually 3:45. So those people who don't comment at the very moment
Right.
feel ripped off. I remember. You finally won the league. All right, we'll get started for the last lecture of the day. Back to Ben.
Great. Well, thank you all for sticking around until the end of today. So let me just remind you real quick what I ended on last time. Just in one picture, we discussed dark matter density profiles in galaxies like our own Milky Way and other galaxies like dwarf galaxies. And the only thing you need to remember is that it goes up. So there's more dark matter as you approach the center of the galaxy, and there's less as you go farther away. I just discussed a little bit how we know this is the case. There are some questions about what happens in here. Those questions are important, but I now want to change gears and ask the question, great, what can we do with this to learn about the structure of dark matter? And so we're now going to change gears, and we're going to be talking about specific dark matter models. We're going to start by talking about WEMP dark matter models, and we're going to ask how can we detect them through their annihilation signatures. So WEMPs, honestly, in my world nowadays, WEMPs are almost a bad word for some reason, because I spend a lot of time thinking about axions, and WEMPs are kind of the competitors. But also, WEMPs are they get a bad rap nowadays. You hear there are papers coming out saying, are WEMPs dead? Which is not good PR for WEMPs. But actually, WEMPs are great. I hope to convince you that WEMPs are still great. And that WEMP dark matter is a really promising paradigm for what dark matter should be. And we could really be on the edge of discovery when it comes to axions, but also when it comes to WEMPs. And so it's a super exciting time to be thinking about WEMPs. And in my opinion, so I'll try to tell you about today, the best motivated WEMP dark matter models, such as those which appear in the context of supersymmetry, the best way of looking for them in the next few years is through dark matter annihilation, what we're going to go over today. So this is stuff, even if you're not working in this field, which I think is very good to know, because there's a chance that you might be hearing a whole lot about this in the next few years as various telescopes turn on, and they either do or do not find WEMP dark matter. So let me just remind you all rapidly about thermal freeze-out. I know that Yonit already went through thermal freeze-out, so I'm just going to go super fast. Essentially, I just want to write down the notation that I'm going to be using, because I'm not sure if it's the same as Yonit's. So first, we have the metric for expanding space-time, which I'm not going to use, but I just want to write down the scale factor. So I'm going to call the scale factor R. So this is in the early universe. So these are our co-moving coordinates, but space-time is expanding. So the scale factor R is increasing as a function of time. What that means is if I have a gas of particles, which are just sitting there, not interacting, then the number density of particles is going to drop off like 1 over r cubed. Because each of my 3 spatial directions is increasing like r, so number densities drop off like 1 over r cubed. The other thing that we're going to need is Hubble, which is r dot over r. OK, that's all I'm going to say about cosmology. So let's now put this to some use. So remember, in this thermal freeze-out story, what happens is that we have dark matter And we imagine that our dark matter can interact with standard model through some question marks into standard model final states. And so at very high temperatures, the dark matter is going to be in thermal equilibrium with the standard model. And then as the universe expands and cools down, this process is going to fall out of equilibrium. It's going to freeze out, and that's going to determine the abundance of dark matter. And so the important plot is the following. Let's plot as a function of time, or as a function equivalently of the mass of the dark matter over temperature, because as we go forward in time, temperature is dropping. So these both go in the same direction. So if I'm going to be plotting n times r cubed, at very early times, what is this thing doing? Is it going down, up, or constant? Constant, that's right. Because when it's going constant, it's in thermal equilibrium. And in thermal equilibrium, since everything is radiation, the number densities are just dropping like 1 over r cubed. And that's true until roughly T equals m chi, the mass of the dark matter. And then what happens is it's still in equilibrium, but now you have an equilibrium distribution for a non-relativistic species. And this becomes exponentially suppressed and goes like the exponential of minus m chi over t, essentially because this process can still happen. Dark matter can annihilate into standard model, but the standard model no longer has enough energy, since t is below m chi, to go this way. So this is not allowed. And that drops down the number density until the dark matter just can't find itself anymore, and it freezes out. And so then you freeze out. And then after here, this is constant again, because now the dark matter is not interacting, so it's just redshifting like I told you up there, and is going like 1 over r cubed. So if I have a larger sigma v, if I have a larger cross section, I'm going to go down more, because with a larger cross section, it's going to be easier to stay in equilibrium. So every time I find another dark matter, it doesn't mean I scatter. I have to compute a probability for scattering. So I have to ask what the probability of scattering is, and that's going to be related to the cross section. So this would be a larger sigma v, where sigma v, I mean the thermally average cross section times velocity. You need to multiply velocity because you want to know what the flux is. If the dark matter is not moving, the cross section could be huge, but it doesn't matter. You're never going to see another dark matter particle. So this is a larger sigma v, and this would be a smaller. A smaller, up, smaller sigma v means you freeze out earlier. Okay, so you can work this all out. It's in my lecture notes if you want to see, but I'm not going to do it because Yonid already did it, I think. Yonid did it. Good. I'm just going to write down the answer. The answer is quite remarkable. What you find is that the cross section to get the correct dark matter abundance is one number independent of mass, which is very non-trivial. If you were to think about this, like, when I think about this, it still amazes me, just looking at this, that the cross section to determine the dark matter abundance is independent of the mass. That's a really non-trivial thing. But you work it out, and you see magically the masses cancel. And so the cross section is about 3 times 10 to the minus 26 centimeters cubed per second. Let's understand the units real fast. Cross section is like, the area of a side of a baseball or something. It's centimeters squared. It's an area, and v is centimeters per second, so it's centimeters cubed per second. Yeah?
I thought this was for some specific mass.
No, this is mass independent. It's the first approximation in this vanilla story. Yeah, which is amazing. It's just a number. We'll see. We'll talk about mass here in a second. In the context of a given model, typically sigma is a function of mass.
Okay, right. Yeah.
But the sigma v, thermally average sigma v, is just a number. It's 3 times 10 to the minus 26 centimeters cubed per second. And this is the really nice thing. This is a target for indirect detection. Because if dark matter annihilated in the early universe to set the relic abundance, then it should still, mostly, for most models, be annihilating today. We'll talk about some exceptions to that. And this sets the scale. 3 times 10 to the minus 26 centimeters cubed per second. In particular dark matter models, Yonit talked about variations to this scenario. This number could be a little bit bigger, it could be a little bit smaller. We'll talk about scenarios where it's actually much smaller for various reasons, but still this sets the scale. This always sets the scale. And this is a target we can then go out and look for today with our telescopes. And so that's what we're going to be really focusing on today and next time, tomorrow, is on understanding how we can use this target to go and try to make discoveries or to rule out this paradigm. So that's where we're going, but we're first just going to have a little bit of an aside. The aside is just going to be to motivate why this number is somewhat special or miraculous, and why people say that this is the WIMP miracle. So I'm going to tell you about this WIMP miracle story and use this as a way to introduce some SUSY dark matter candidates. In particular, I'm going to tell you why I think the Higgs Xeno is kind of the best WIMP that we have standing. I'm making some very strong statements here, but I think that's what you need to hear. You need to hear people's opinions. So I'm going to tell you why I think the Higgs Xeno is a great dark matter candidate to be thinking about for the next few years. Okay, so the WIMP miracle. So the WIMP miracle is relatively straightforward. It's just to say that this cross-section is naturally achieved for electroweak scale mass particles and electroweak scale interactions. So what do I mean by that? Let's consider the following process, where dark matter is some fermion, and it's annihilating to the standard model through some diagram that looks like this. And let's put some coupling constant in here with the standard model, GD. And this could be GD. And let's say that this thing has some mass m. So its propagator goes like 1 over m. So then sigma v, the cross-section, is going to go like just dimensional analysis. We have a 1 over m here. So the matrix element is going to go like 1 over m. Then we have to square it. And then we have the coupling showing up twice. So this is going to go like some alpha d squared, because it's g squared squared, over m squared, just roughly, leaving off all the order 1 numbers. Does that make sense? Not m to the 4th, because it's a fermion. So this propagator is going to go like 1 over m. OK, so then you just put in some numbers here. So this thing is supposed to be equal to 3 times 10 to the minus 26 centimeter cubed per second, where I'm saying v is about 1 at the level that I'm working in natural units. So 3 times 10 to the minus 26 centimeters cubed per second, I can write this as a few times 10 to the minus 4 over 1 TV squared. And so this tells me that I need alpha d around 10 to the minus 2 if I have m chi around a TV. And this is awfully close to the electroweak scale. And this thing is awfully close to the coupling constant that we have for the weak force. So it is possible that the dark matter is literally in a representation of SU2 left across U1. So your dark matter can literally be weak in the sense of the weak force, which is very non-trivial that it all kind of works out this way, and is why people say the WIMP miracle, and it kind of motivates the mass scale for WIMPs on the order of hundreds of GeV to kind of few TeV. And so what we're going to go to now is to look at what some explicit candidates are for WIMPs. So this is very general. We're not saying anything specific, and I just want to show you how WIMP candidates appear naturally in the context of supersymmetry. Yeah?
Do people ever think about bosonic WIMP candidates, or would it not be a WIMP anymore?
Yeah. You can have the thermal freeze-out scenario for bosons too. I mean, sigma v is always going to scale the same way, because then you're going to have an energy which enters somewhere else, and energy is of order m, up to the level I'm working. So it's always going to kind of come out the same way. Yeah.
When you're talking about these higher reps of SU2, have all these things just generally been classified, like all possible representations of SU2, all possible masses that we could consider, and things like that? People have charted that out?
Yeah, good. So the question is, have people kind of charted out the landscape of if you're a representation of SU2 given the representation, what mass are you and so forth? And the answer is yes. I mean, yeah, actually, yes. There's literally a paper which did this, which I can point you to afterwards, which said, here's the representation. What is the cross section? What is the correct mass? But supersymmetry naturally gives us kind of the first two. It gives us a dark matter particle candidate in the fundamental of SU2 and the adjoint of SU2. And so we're going to look at those now. But then you can just, as an exercise, you can then continue this on to arbitrary representations. Okay, so supersymmetry. I am not going to say too much about supersymmetry because supersymmetry, well, let me just say these words. One reason to talk about supersymmetry is the hierarchy problem, why the Higgs mass is so light. And the hierarchy problem, naturalness, another name for this, is going to be the subject of one of the lectures, 4 lectures next week. So we've coordinated, and you're going to hear a lot about supersymmetry in the context of naturalness and supersymmetry as a construct next week. So I am just going to kind of briefly go through supersymmetry, just picking out the parts that I need for the dark matter story. So there might be some gaps here if you haven't seen supersymmetry before, and that's fine. Those gaps will be filled next week. Okay, so in kind of the MSSM, the Minigal supersymmetric standard model, what you have is for every boson, you have a fermion. For every fermion, you have a boson. Or supersymmetry is a symmetry which exchanges bosons and fermions. That's one way of thinking about it. So all of the boson particles that you know of in the standard model, you should think that there are superpartners, which are going to be fermions. For all the fermion particles that you know of in the standard model, there are going to be bosons. And the properties of these bosons and fermions, apart from their spin, should be exactly the same. So they should be in the same representation of the gauge group. They should have the same number of degrees of freedom. And they should have the same mass. That's a problem, because do you see a supersymmetric electron out there with the mass of the electron? No. So supersymmetry has to be broken at some scale, which is going to push the superpartners to be heavier than the standard model states that we know of. So supersymmetry is broken. It has to be. And that's fine. There are ways of breaking supersymmetry spontaneously and communicating that to the standard model. But I'm not going to go into that. But you might hear some about that next week. Yeah?
At some scale, is the MSSM also SU3 cross SU2 cross U1?
Good, yes. The gauge group is the exact same as the standard model. And the standard model particles are all there, with one small caveat, which I'll mention. And but you add extra stuff in. And some of that extra stuff can be WEMP dark matter. So what do we have? We have our W bosons in the standard model. In the context of supersymmetry, we're also going to have Xenos. There are great names here. So let me write down the boson. And then I'm going to write the spin-a-half particle. And then I'm going to write SU3 cross SU2 cross U1. Sorry, if you can't read that, it's just SU3 cross SU2 cross U1 representations. So for the bosons, we have the W bosons. And for a spin-a-half, we have, which are in the adjoint, I'll write that down in a second. And then for the Xenos, we have W tilde plus or minus, and W tilde 0. So what's the representation? It's a singlet under color. It's adjoint of SU2, and it has 0 hypercharge because it is the gauge boson of SU2. So by construction, it's an adjoint of SU2, and it's not charged under U1. So then there's the B boson, whose superpartner is the Bino. And so we have B0, which I'm writing down to mean that it's electrically charged. So if I'm writing a plus or minus or a 0, I'm going to refer to eventually the electric charge after electroweak symmetry breaking. In the Beano, you just put a tilde, so you start to notice the pattern. You put a tilde on the superpartner. And this is in what representation? Yeah, this is 1, 1, 0. It's the singlet. It is the Goldstone boson. It is the gauge boson of U1Y. Then there's the Higgs. And there are the Higgs Xenos. And here's where things get a little bit complicated. So in the standard model, there's just one Higgs doublet. In supersymmetry, you need 2 Higgs doublets. And there are formal ways of seeing this when you talk about the superpotential and properties that it must have. A more down-to-earth way of seeing that you need to have 2 Higgs doublets is the following. When you have 2 Higgs, let's suppose we just had 1 Higgs doublet. Well, it's going to come with a Higgs Xeno, which is a fermion. And that fermion is going to be in a non-trivial representation of the standard model. And so anomaly cancellation is going to get messed up. Because if you've gone through anomaly cancellation in the standard model, it's a miracle that it works out. And you add in another fermion, and it's just not going to work out. So you add in 2 Higgs doublets, essentially with opposite properties, such that the standard model remains anomaly free, or the MSSM remains anomaly free. That's kind of a very pedestrian, down-to-earth way of seeing why you need 2 Higgs doublets. So we have now our 2 Higgs doublets, HU plus and HU0, which will couple to kind of up-type fermions. And then we have our Higgs Xenos, H tilde, U plus, H tilde, U0. And these are 1, 2, 1/2. And then we have our down-type Higgs, which is H D0, H D minus. Again, these refer to the electromagnetic charges. And then H tilde D0 and H tilde D minus. And this is in 1, 2, and minus 1/2. And when I said kind of to you before, I meant because there's 2 Higgses. But the standard model Higgs is going to be some linear combination of this, and you're going to get other heavier Higgs boson states, which will also be there. Is that going to be your question? OK, awesome. So, yeah.
Maybe something very basic, but I understand that with supersymmetry you can solve some problems. But suppose I had a similar model where it's not supersymmetric, but more or less the same. Wouldn't it solve the same problem?
There are other ways of, so the main problem, one problem that supersymmetry is trying to solve, which we're actually going to give up on in a second, is naturalness. Is why the Higgs mass is so light. And next week you're going to hear many other solutions to this problem. And for example, there's neutral naturalness, which is okay, so first let me just say what I was going to say next, which is I haven't written down everything, but I'm going to stop the list here because I need to write down the standard model fermions and I need to write down their scalar superpartners. Those scalar superpartners, like the superpartner at the top, is going to be strongly interacting. And that's bad in the sense that it makes it easier to look for. Why is that bad? You'd think that's a good thing because we've looked for these superpartners and we haven't found them yet. So you can try to hide the supersymmetric solution to the hierarchy problem by removing bits that you actually don't need. Of course, then you lose some of the theoretical beauty of it and the original theoretical motivations for why you should be considering supersymmetric constructs in the first place. But you can construct more minimal solutions to the hierarchy problem, essentially just by canceling off these quadratic divergences that you get when you calculate the quantum corrections to the Higgs mass. I'm speaking fast here because I know that you're going to see this next week. Yeah.
I just want to make sure I understand that HU plus and HU0, are those each one component of each of the separate doublets?
Yeah, so these are they're doublets of SU2, so I'm writing down their components. So these are each, these are complex scalar fields. And this is a Weyl fermion, a single one, and it's in a doublet, but I'm writing down both components of the doublet. Similarly, I'm writing down all the components of the adjoint, but each of these things are Weyl fermions.
Okay, so I could understand like HU plus and HU0 as one doublet?
That's right.
A doublet, a doublet, and a doublet.
Yeah. Like this, if you weren't talking about supersymmetry, this would be the standard model Higgs doublet with 4 degrees of freedom. Cool. So I'm not going to talk about the fermions for a reason which I'll make clear in a second, but let's just go with this for a second. So what's going to happen is after electroweak symmetry breaking, you have the neutralinos, they're called, which are the neutral fermionic friends, counterparts. So you have the Xeno, the neutral component of the Xeno, the Bino, and then these Higgs Xenos. And generically, they're all going to mix together. And so generically, what you find is that below electroweak symmetry breaking, you have a Lagrangian for the neutralinos. And this Lagrangian is going to have a mass term. And this mass term is going to in general be off diagonal. And so this vector here, which I'm writing down psi mu, psi 0, this is all of these neutralinos. So we have the Bino, the Xeno, neutral Xeno, and the Higgs Xenos. So in supersymmetry, the lightest neutralino, so these are all going to mix together. You're going to have 4 Majorana mass eigenstates. And the lightest mass eigenstate is, if it is the lightest supersymmetric particle, it is going to be a dark matter candidate. So the lightest supersymmetric particle, if it's one of these neutralinos, well, it's generically, unless it's a charge Xeno, which typically the charge Xenos are heavier than the neutralinos because they would otherwise be degenerate, except for electromagnetic corrections below the scale of electroweak symmetry breaking, which tend to make them a little bit heavier. So typically the neutralinos are almost the same mass as their charge Xeno cousins, except the charge Xenos get radiative corrections, which tend to push them up a little bit in mass. So the lightest neutralino, lightest mass eigenstate here, can be a dark matter candidate. And so that's what we're going to look at, the lightest neutralino as dark matter. So it turns out, for example, and I'll write this down in a second, that if dark matter generically, your lightest neutralino is going to be some admixture of Bino, Xeno, Higgs Xeno. But it's a good idea, and especially motivated in the context of the model I'll tell you about in a second, to consider the case of pure Bino, pure Xeno, pure Higgs Xeno dark matter. And in this case, everything is determined because these things are in representations of the standard model. So you can calculate all of their cross sections for annihilation into the standard model. And then you can see what sigma v is, and you can find the mass of the dark matter candidate. And I can tell you precisely what it is. So for example, for a Xeno dark matter, the mass is about 3 TeV. And for Higgs Xeno dark matter, the mass is about 1.1 TeV. It's an incredibly predictive statement because everything is calculable since these things are in representations of the standard model. And these numbers shouldn't be surprising because we just derived this from the Wemp miracle. With an SU2 kind of strength coupling, the difference between 1.1 and 3, these just come from like Clebsch-Gordon-y types of coefficients from these things being in different representations of SU2 cross U1. It's nothing miraculous. There's a little bit more complication there in something called Sommerfeld enhancement, which we'll talk about later. But roughly speaking, everything is just set by the representation. And to answer whoever question it was before, yeah, you can keep this going. In some sense, you can think of the Xeno and the Higgs Xeno as being supersymmetric dark matter candidates, but you can also just think of them in a more minimal way, which is you add in some new state and some representation of the standard model, you look at the neutral component of that, and then you can go calculate its relic abundance. Yeah?
You kind of alluded to this, but is there some reason to think that these pure states are going to be our lightest neutralino, rather than like a combination of states?
Yeah, good. So Yeah, so it depends. I mean, in the context of the model that I'll tell you about next, yeah, typically your lightest neutralino is kind of mostly Xeno or mostly Higgs Xeno. If the scale of, essentially it depends on what the mass is. This is going to be some matrix. It's going to have some off-diagonal components and some diagonal components. You're going to ask the question, how big are the diagonal components compared to the off-diagonal components? So I'm going to just tell you briefly about split supersymmetry. And in split supersymmetry, the diagonal components are typically pretty big, such that you typically end up with just like, you have large hierarchies, and you typically end up in pure Xeno, pure Higgs Xeno. But if you have a lower scale of supersymmetry breaking, then yeah, you're typically just going to get some mess of all of these things mixed together, and then you have to go calculate it for that scenario. Yeah?
Could you comment on the mass of an n-dimensional SU2 representation?
On the mass and what, sorry?
Of an n-dimensional SU2 representation?
Oh, you'd have to compute it. Like, how does it scale with n? I have no idea. But it's...
This is the minimal dark matter story.
Yeah. Yeah.
And so as you enlarge the size of the SU2 multiplets, you have more annihilation partners and stuff like that. And so you push the masses to higher and higher values in the multi-TeV range. But the story is largely similar to this.
Yeah.
So you have a bunch of particles that participate in the freeze-out process.
But it stays in the TeVS range?
Yeah, multi-TeV. So, but there are, at some point you got to stop because you have a lambda hole that gets, closer and closer the larger the representation. Right. So, it's a game you can play up to roughly, I think, at dimension 7.
Okay.
Yeah. Yeah, I have no idea. Yeah, the n goes to infinity limit. I have no idea how that behaves, but yeah. And let me just comment on one thing that Stefano mentioned. The freeze out is a little bit more complicated because of co-annihilations, essentially because the charginos are nearly degenerate in mass, so they can kind of co-annihilate in the early universe. But you all heard about co-annihilations last week, so I'm not going to talk about that. Yeah. Oh, yeah. Go ahead.
We've seen this plot a couple times throughout so far. This plot of collider constraints on new physics.
Mm-hmm.
They tend to rule things out up to about a T.
Mm-hmm.
Is the Higgs Xeno dark matter threatened by those?
No. In fact, Higgs Xeno dark matter is really hard to see. The colored states are much easier to see, and those are the ones that kind of get pushed up farthest because they're produced more readily and then they're easily observed. But Higgs Xenos, like the thermal Higgs Xeno, is incredibly hard to see at colliders. I think it would even be hard to see. I think there are papers saying it would be hard to see at 100 TeV collider. And also it turns out that in typical scenarios with typical mixtures, Higgs Xeno dark matter is incredibly hard to see at direct detection. It's below the neutrino floor. So indirect detection is what you need. And I'll show you that Higgs Xeno dark matter we're going to get there. Oh, there's a question in the back. Yeah, so these numbers, right. So, in the case of essentially pure Higgs Xeno and pure Xeno, these numbers are what they are. They're just representations. They're just minimal dark matter representations of SU2 across U1. Okay, so there's a problem with supersymmetry. Oh, first let me just say, Xeno dark matter is essentially gone at this point. Why? From indirect searches, which are really powerful in this mass range. And barring a large dark matter core, which we discussed last time on Monday, barring a large dark matter core, which we don't really expect for the Milky Way, but who knows, this is just not there. But this one is. Okay, so let me tell you now another sad face. Supersymmetry is in trouble. It's probably not news to anyone. Because supersymmetry is originally invoked to solve the hierarchy problem, or that's one reason to talk about supersymmetry is the hierarchy problem. And given constraints on superpartners, there is tuning. There's some amount of fine tuning right now in a completely natural solution to the hierarchy problem. And that's a huge result. It's a transformational result which the LHC has helped produce, which is it looks like, unless we haven't thought of something, which is possible, it looks like our universe has some amount of fine-tuning. And that's crazy, right? That makes you think about the multiverse and all sorts of weird things that you didn't want to think about, but you're forced to think about them because of the data. But then you might say, like, why am I talking about supersymmetry in the first place? There are two answers to that. One, this is just an example of minimal dark matter. You can think about it through that lens. But also, supersymmetry does other nice things other than just solving the hierarchy problem. For example, you might have seen in your kind of field theory or standard model classes that all the gauge couplings kind of seem to unify. But they don't really unify. They kind of all cross. You have three curves, one for SU3, one for SU2, one for U1. And they kind of cross, but they don't really cross. They like make some weird triangle. And what you'd really like to, and that real weird triangle also is kind of low in mass. It's about 10 to 15 GeV, which is, in the context of grand unification, is a bit of a problem for proton decay. But in the context of supersymmetry, miraculously, all of these lines, now the beta functions change because you have new states, they cross at a point. And that point is closer to 10 to 16 GeV, and now your gut theory is compatible with proton decay. And it's amazing. Like, it's worth going through it. It just takes these lines, which are making some weird triangle, and it collapses them down to a point. And this, historically, is one of the really compelling reasons, in addition to the hierarchy problem, for why to be thinking about supersymmetry in the first place. Another nice feature of supersymmetry is it gives us a dark matter candidate. So it's doing three things for us. It is solving the hierarchy problem, it is giving us gauge unification, and it's giving us a dark matter candidate. So I'll come to you in 1 second. So this motivated people to talk about a construct called split SUSY. And split SUSY, this is from James Wells, Nima, Ahmed, Savas Dimopoulos, John Giudice, and others, back around 2003, 2004. There's a whole sequence of papers that are really interesting to read. I encourage you to take a look at them. And what they said was, let's keep gauge unification. And let's keep dark matter. But let's forget about solving the hierarchy problem. So how do we do this? Well, you don't want to completely forget about solving the hierarchy problem, but we're going to not solve it completely. So the idea is going to be left with some hierarchy, because we know from data that there is a hierarchy. So let's just stop trying to fix that hierarchy exactly and just accept some amount of small fine-tuning. But we want to keep gauge unification, we want to keep dark matter. And one way of doing this, it turns out that these are the only particles you need, along with the gluinos, which I'm not writing down here, which are the superpartners of the gauge bosons. You only need these particles for gauge unifications. The superpartners of the matter fields, they're shifting the beta functions all in the same way, but they don't affect this thing ending in a dot. And since those are scalars, the superpartners of the standard model fermions are scalars, it's natural to decouple them. So to assume supersymmetry is broken at some high scale, and those scalar superpartners are stuck at that high scale of supersymmetry breaking. And then these fermionic components, these fermions, are for whatever reason protected a little bit, and so they show up a little bit lighter, maybe an order of magnitude or 2 or 3. And so that's the idea of split SUSY. And in the context of split SUSY, it does, since there are large hierarchies, it does kind of make sense to be talking about pure Higgs almost pure Higgs dark matter, almost pure Wino dark matter. And as I said, Wino dark matter seems to be gone, but Higgs dark matter is still there. And so this is personally my motivation. I'm essentially just telling you philosophy right now. This is my motivation for spending time thinking about Higgs dark matter. Is I personally find this story of split SUSY to be very compelling, to explain problems that we see out there in data. You are forced to give up a little bit of fine-tuning, but there's a cosmological constant. There's all sorts of fine-tuning problems that we can't just completely ignore. And maybe the universe just fine-tunes a little bit. Maybe there is some multiverse and there's some amount of fine-tuning, But even in that scenario, who knows? Maybe the multiverse has some reason to prefer there to be supersymmetry at a somewhat lower scale, but things don't have to be completely natural. So to imagine supersymmetry is broken, not at literally the electroweak scale, but at 10 TeV or 100 TeV, I think is not that crazy, which is kind of what you need in this context. You had a question?
I don't want to back us
Okay.
too far. Thanks.
Yeah.
So what do you think about approaches to the hierarchy /naturalness that rely on like criticality and like self-work? Like Yoni had a paper on this, and like certain folks had a paper on this, and it kind of maybe pulls this out of your issue. Like it just makes it not a problem. Right? It just takes it away from this particular type of question.
Good. So the question was, what do I think about solutions to the hierarchy problem that are based on criticality? And I think they're fascinating, and you're going to hear some about this next week. But I don't want to digress into solutions to the hierarchy problem because I want to get on to how to detect these things. But we can talk about this more offline to hear kind of more about my opinion. Yeah.
So, if I understand correctly, with Suzy, you just letting the scale of Suzy be high, like higher than the scale.
That's right. You let it to be high, and then you assume that the scalars are at that scale. The scalar superpartners and the fermionic superpartners are protected a little bit for reasons which I'll just refer you to these papers about, and they remain lighter.
So in that case, how high can you let it be and still have like the Xeno be a bit?
Good. So the Higgs Xeno mass is fixed by dark matter. Because remember, we want to keep dark matter. So this thing needs to be 1.1 TeV just to explain dark matter. I mean, that's just an observational constraint if we want to keep 1 and 2. From your theoretical priors, maybe you would have expected it to be heavier, but it can't be because we wanted to explain dark matter, at least in the standard cosmology.
Yep. But in that case, like, is the scale of Suzy breaking just completely independent, or is there like an up or down?
Yeah, good. You can try to kind of, it's not completely independent because you need to also match the Higgs mass. And this gets into a whole story, which I don't really want to go down into. But given kind of the top mass and the Higgs mass, that kind of constrains the scale of supersymmetry breaking within this context. And it's, somewhere around 10 TeV to 10 PeV roughly. But I would need to digress a lot to get into that. Cool. OK, so let's leave that aside. This is just an introduction. This is meant to be an appetizer to go look into these things more. Let's just talk about Higgs Xeno dark matter for a second. So Higgs Xeno dark matter can annihilate. So we have annihilation. And it can annihilate by forming a diagram just like what I drew, except now I can tell you, for example, you're going to have a W plus, a W minus, where this is a chi0, and this is a chi0, and this needs to be a chi minus, where this is the charge Xeno. So for the Higgs Xeno, this would be one of these charged Higgs states. And you expect this thing to be a little bit heavier, maybe about 100 MeV heavier. Why is it heavier? Because at the scale of electroweak symmetry breaking, these would have the same mass, but then there are electroweak corrections to its mass, which is push it up in a calculable way. But still, it can participate in this diagram. And this thing, for this particular Higgs Xeno dark matter, it's going to have a cross mass. It's going to have a cross section right around 3 × 10⁻26 centimeters cubed per second. But so this annihilation is going to give you W's. But you can also have a loop process, which looks like this. So we have chi0 or dark matter, and then we have a W, and then we have some chi plus or minus, and then we have photons. Essentially, since these things are charged, they can emit photons. Our dark matter neutralino can't because it's not charged. So if we want to emit photons, we need to calculate something at one loop. And so this is going to have a smaller cross section than that. And it's smaller because we've inserted E here, and we have a loop factor, and E is about 1/3. So we get 1/3 squared, and then we square that to get the cross section, and then we divide by some pi's because it's a loop. And so this process, this cross section, is going to have sigma v much smaller than 10 to the minus 26 centimeters cubed per second. So why am I talking about it? I'm talking about it because this one turns out to be easier to look for often than this process. Yeah?
So what assumptions are you making about psi 0 here?
For the purpose of this, it could be kind of any of these neutralinos, because generically they're going to have some charge Xeno counterpart. But yeah, this thing, for the purpose of what I have in mind, you should just think of this as the Higgs Xeno, the neutral component of the Higgs Xeno. Okay, so what does the spectrum from Annihilation look like from this? It looks like a continuum of gamma rays plus a line. So I should say first, because I didn't mention it, I am just going to be interested in the gamma ray signals that come out of this, because the gamma rays are what's going to be easiest to look for with telescopes. So what happens is that, well, from that loop process, you produce gamma rays, because they're photons and they have energy of about a TeV. So that's what we call a gamma ray. For the W bosons, they're going to decay, because these are unstable particles, and they're going to get decay, and they're going to produce a whole bunch of stuff. In particular, they're going to produce pions. And they're going to produce pi zeros, and pi zeros decay into photons. So you are going to get a lot of gamma rays which come out of those Ws. But because of kinematics, because of how these things are decaying, and they're decaying to many daughter particles which are then decaying, you're going to get a continuous spectrum of gamma rays. You'll also get charged cosmic rays, which Stefano mentioned earlier. But those are a little bit harder to look for. So we're not going to look for them. Because we only have a set number of days. So we're going to look at the gamma rays. Why are gamma rays easier to look for? Because they point. You can just follow them back to where they came from. Whereas charged cosmic rays are going to go on some meandering path through the galaxy with all the magnetic fields before they finally hit us here today. So let me just draw one picture. I'll get to your question. So then the spectrum that you expect to see is something like this. So this is dn gamma d log x as a function of x, which is the energy over the mass of the dark matter. And you expect to see some continuum until 1 plus a line. And that line is coming from the loop process, and the continuum is coming from the tree level process. Yeah?
You might have said this and I missed it, but why are we expecting gamma ray frequencies? Why not like some other frequency?
Good. So because the mass is a TeV. And so the characteristic energy scale is going to be about a TeV, and TeV is gamma ray. So, and this thing is going to be some spectrum, but you know, we're starting at a TeV, so we count gamma rays starting at about an MeV. So we've got a lot of space where we're still producing gamma rays. It keeps going down, so eventually you'll mix some things you call X-rays, but that's going to be a tiny fraction of the energy.
And then I guess just to follow up, is that TeV, is that like a solid prediction it must be TeV?
For the Higgs Xeno, it is. It's 1.1 TeV. Okay. Yeah, so for this, for the WEMP type dark matter, where you have in mind the weak scale, so you're fixing that alpha D essentially, then M needs to be of order TeV. If you allow yourself to decouple these things and imagine that dark matter is interacting in some other way that's not the weak force, then you know you could start playing with alpha D and M simultaneously. And then you could move M around a little bit more. But in the literal weak form of WEMP, then yeah, it's around the TeV scale, or GV, hundreds of GV TeV scale. Yeah? Assuming it's all of dark matter and assuming the standard cosmology. Yeah. Yeah.
Well, listen, from Unix lectures, we kind of heard about towers of states that we could have, and a bunch of stories about how you don't have to actually couple the whole thing, but you still get the same rate.
Yeah.
So I guess when we're talking about SUSY, a kind of natural tower that I think about would be n greater than 1 SUSY. And so are the bounds on those things also kind of similar?
N greater than 1 SUSY has some issues for phenomenology. So it would need to be broken at some much higher scale. But yeah, you do have towers of things. Like we have the charginos, which are nearly degenerate, so you get co-annihilation, which I think that Yoni talked about. And this is an example of how that actually comes out into play. So that 1.1, if you want to get the 0.1, you need to account for co-annihilations. So a lot of the things that she talked about come out explicitly. She talked about them in generality, but they come out explicitly in this context. Yeah, okay, so that's the motivation. We're going to be looking for gamma rays. So now we're going to change gears, and we're going to start to talk about how you can look for gamma rays from dark matter annihilation. Because the punchline is, we are not quite there yet for Higgs Xeno dark matter, but we will be soon. And so I want to try to convince you of this. But now we're going to take a step back, and we're just not going to be talking about Higgs Xenos. We're just going to be talking about WIMP dark matter annihilating. So I just want to talk generally about dark matter annihilation. And in fact, we're also going to mention dark matter decay. So we're just going to talk about astrophysical signatures and gamma rays from annihilating and decaying dark matter. Although for most of the time, we'll be talking about dark matter annihilation. And then after I tell you that, kind of the formalism for this, which you also need in order to do this problem from analysis of segue data, we'll then come back and talk about the Higgs Xeno in this context. Okay, so let's now talk about WIMP dark matter indirect detection. Okay, so the quantity which I'm going to start by computing is I'm going to call it gamma over V. And this is going to be the dark matter annihilation rate per volume. So this is going to be a quantity with dimensions 1 over second, 1 over centimeter cubed. So the question is, and I'm talking about today, I'm at redshift z equals 0. I'm in the Milky Way or some other galaxy. If I have some dark matter, what is the number of annihilations per second per centimeter cubed? And so this we expect to scale like n squared times sigma v, where n is the number density of dark matter wherever I'm looking in the galaxy, and sigma v is the annihilation cross-section. So why is this n squared? Well, imagine you're a dark matter particle. You need to find another dark matter particle. So that's a factor of n. But you yourself are a dark matter particle, so that's another n. So you get an n because you're finding 2 dark matter particles to come together and annihilate. And then there's the cross-section, the chance that they annihilate in the first place, and the velocity, because they need to be moving, or else they're never going to encounter each other. In fact, this should really be 1/2. The reason the half is there is because if we're imagining the dark matter are indistinguishable particles, then you're overcounting n squared sigma v. So you can draw a picture and try to count things. Draw a finite number of dark matter particles in some box and just count it, and you'll be convinced that there's a 1/2 there. So I'm not going to draw that picture. Try to convince yourself that there's a 1/2. Yeah.
That's gamma over v.
That's gamma over v. That's right. So you can convince yourself of the units. This is 1 over centimeter cubed for n. Says 1 over centimeter to the 6. And sigma is v is centimeter cubed per second. So that works out. 1 over centimeter cubed, 1 over seconds. Cool. So another aspect about dark matter annihilation, so this is kind of 1. And then 2 is it's isotropic. That means that my dark matter, they're coming together and annihilating, and they're producing gamma rays, which are going in all sorts of directions, but there's no preferred direction. It's just isotropic at any point in space. So that means that I can write down 1 over volume d gamma d omega, which is the per unit volume, the differential annihilation rate in some units of solid angle. And since this is isotropic, this thing should just go like 1 over volume and then gamma over 4 pi, essentially, because it's just 4 pi distributed. Maybe I'm missing some omega here. Probably am. But anyways, we're not going to use this formula. You get my point. It's isotropic. So, and this thing is d. When we talk about d gamma d omega, this brings in a steradians. Cool. So now let's combine all of these things together. This is 1, 2. There's one other kind of point about dark matter annihilation that I just want to write down, which is that we're going to generically make a continuous spectrum of gamma rays. And that continuous spectrum of gamma rays for a given dark matter annihilation, I'm going to define by a function, which is dn gamma, de gamma. So this is the number of photons per energy per annihilation. So if you integrate dn d gamma dn de over E, you'll get the total number of photons that you generate per annihilation. And if you multiply an E before you integrate, you'll get the total amount of energy which is injected into photons per annihilation. And that total amount of energy should be less than or equal to 2 times the mass of your dark matter particle by energy conservation. Okay, so the quantity which we're going to compute, I'm now going to call phi. This is going to be a flux. And this thing is it's going to be a function of energy and some angle psi, which is the direction that I'm looking at. So now we're imagining we're an observer here on Earth, and we're looking at some direction on the sky, which I'm denoting by psi. So psi really should be 2 angles, but I'm just going to call it by 1 angle. It's just the direction I'm looking at. And this thing is going to be the differential number of photons which I'm detecting, or which are passing my detector, per energy, per time, per unit of solid angle, and per area of my detector. So let's make sure that we understand everything here. In gamma is the number of photons that pass through our detector. Our detector has area A. And it's looking out over the sky, over some region of solid angle, d omega. dt is the amount of time that we're integrating over. Do all of the quantities here make sense? Okay, so then the question is, how do we compute this? What is this thing in terms of astrophysical parameters, like the cross-section and like the dark matter density and the mass? We want a formula for this. So the formula, well, what you can think of is you're the observer, and you're looking out over some unit, some d omega, and you're looking at a blob of dark matter. So what we want to be doing is we want to discretize this into little boxes. In each one of these boxes, we write down our gamma v, and then we just sum all those boxes up together. So we want to know how many boxes are there within our d omega, and then we're going to just sum up those gamma v's for each little box. Yeah?
If the dark matter is isotropic, why do the boxes?
Good, because we are not. So at a given point in space, the annihilation is isotropic. But the distribution of dark matter is not isotropic.
Okay.
And so when we're looking out of the Milky Way, there's more dark matter over there than there is over here. Or probably there, I guess, there's more dark matter, depending on where south is. There. Someone can check that, where the galactic center is. Okay. So cool. So this thing, you can think of calculating it as 1/2 sigma v. There's going to be a mass of the dark matter squared. So first, 1/2 sigma v is just that 1/2 sigma v there. 1 over m dm squared is going to come from the fact that there's a number density here, but I prefer to talk about energy densities, because energy densities are what we measure in astrophysics. That's what we talked about last time. And number density is just energy density divided by the mass. So That's 1 over mdm squared. Then I'm going to have an integral dr r squared. And then there's a rho squared of r. So the rho squared of r is the n squared, but with the 1 over m taken out. And I'm not integrating over omega because I took it out and I put it in the denominator over on the left-hand side. But otherwise, I would have an integral over d omega. And then I need to have a 1 over 4 pi r squared flux fall-off factor. So the only confusing part might be, where does the dA go? And what you can think of is the dark matter is annihilating isotropically. And our detector has some area A, but the emission is distributed isotropically over some sphere of radius r. So the fraction which we see, the fraction that we see is A over 4 pi r squared, or I guess I'm writing it as dA. And so I just essentially inserted that fraction here and then divided by dA to get the dA in the denominator on the left-hand side. So then miraculously, these r squareds cancel. And we then end up with this very famous formula, which you will see over and over again if you work in this business. And it is that this phi, this flux for E and psi, this is dN gamma, dE gamma, and then sigma V over 8 pi m dm squared, then the integral dr of rho squared of r. And it's convenient to define this thing as J. This is the J factor. And this encompasses everything that has to do with astrophysics. And this encompasses everything that has to do about particle physics. And the very nice thing is that these two things factorize. So let me just, this is an important thing, so I'll just write it again. The J factor, J of psi, depends on where you're looking, is defined as dr of rho squared of r, where r is starting from Earth and it's integrating out. These are spherical coordinates centered on Earth. Any questions about this? Yeah.
Where is the angular dependence?
The angular dependence comes through this J.
I just don't see it in that expression.
Good. So this rho, it's a function of r, but it's also a function of which way we're integrating out. So really, it's also a function of psi. Yeah, sorry. I could just write this as r comma psi. So everything about the direction and the radial dependence, yeah, radial, again, is from Earth. All is encompassed in this J factor. Yeah?
So if rho was a density and we actually looked at integral just rho, that's kind of like the amount of dark matter that we're looking at in the direction, and that's fixed by experiment, right?
That's right.
So this is a quantity that basically represents the fluctuation, density fluctuation. Is that correct?
Yeah, this is a density fluctuation. So, so what I'll mention real fast next is what happens for decay. And for decay, it turns out that you're just sensitive to the amount of dark matter. But for annihilation, yeah, you are rewarded by having dense places, even if it's the same dark matter density. So to connect to something that we talked about last time, which is substructure. Substructure can be very important for annihilation, but it's typically not important for decay. And that's because substructure enhances rho squared for a fixed rho. When we go through this for decay, you'll see that doesn't actually, decay doesn't care. Yeah? One of them has a what? Sorry? Oh, yes. Thank you. Yes, definitely. Because there's a DND gamma on the right here. So yes, thank you. This should have a let me just put it right here. Thank you. That's a DN gamma, DE gamma. It is the number of photons per energy per annihilation. Yeah. Yeah.
In that case, I'm a little confused actually about where the rate and volume came in.
The volume was canceled. The per volume was canceled by this volume because I'm integrating over a volume element.
I guess I just don't see it in the first expression you were about to flux.
Good. This doesn't, so this, you mean this line here?
Yeah.
Yeah, so here we don't care about volume because we're looking out at some d omega and we're going to integrate out to infinity. And so we're the volume is an infinite that we're integrating out of. But what we do is we discretize this into a bunch of volume elements and we sum them all up. And each of those volume elements has that 1 over v d gamma d omega, but then we have to integrate. And so the integrand or the measure factor is what you're seeing here.
Those 8 to d, because the annihilation is proportional to the number of matter.
Yeah, good. So there's two dn gamma, dn de's, which I think is getting confusing. This is the number which are detected or crossing our detector. This is the number per annihilation. So these are different quantities. So this is the spectrum, which I sketched over here. And this number is the number which actually cross our detectors. That depends on the observation time and on the area and everything else. They're different ends. OK, so let me just mention real fast that this whole thing would carry through trivially for decay. And I'll mention next time why I think dark matter decay is also a very well-motivated scenario to consider. But let's just forget about the motivation for a second and just talk about the visible signatures. So if you have dark matter decay, then maybe while I'm erasing, just think about this. What are you going to replace gamma v with? So gamma per volume. So the annihilation rate, the rate per volume. This is going to be replaced by something. And what is that something? So just think about that while I'm erasing this. OK, so that is for annihilation. We had the annihilation rate per volume, which was 1/2 n squared sigma v. And remember, this is something with units of 1 over second, 1 over centimeter cubed. So for dark matter decay, the analogous quantity, gamma over v, I claim is n times the annihilation rate. Sorry, the decay rate. Decay rate. And the decay rate is just 1 over the lifetime. Just check the units. This thing is 1 over centimeter cubed, and this is 1 over second. So the units work out. 1 over seconds, 1 over centimeter cubes. And indeed, this is a more trivial case, right? Because you just say, OK, I have some box of particles. How many particles are there in that box? That's what's given by the number density. How many decay in a given time? Well, that's given by the decay rate. So it's a bit more trivial to work it out in this case. And then we see that for decay, all we have to do is substitute. Instead of writing down this, we write down n gamma. And so for decay, the flux is given by dn gamma, de gamma. That's still the same. And then gamma, the decay rate, over 4 pi m dm. And then the integral dr now of rho of r. So the two differences, well, 3. There's no cross section. Now there's a gamma decay, the decay rate. There's no 8 pi. Now it's 4 pi because we don't have the 1/2 symmetry factor. And instead of 1 over mdm squared is 1 over mdm because we only have one factor of n. And since there's only one factor of n, we just integrate rho. We don't integrate rho squared. And so for decay, we define a d factor. And d factor, d, is defined as the integral dr of rho of r. And I have spent many of my professional working hours calculating d factors and j factors. These things are super important because they tell you the size of your signal independent of whatever particle physics model you have in mind. Any questions on this? Yeah?
Would you expect different galaxies to have different j factors?
Yeah, I mean every galaxy is going to have a different dark matter density profile and different total mass, different scale radius. So yeah, these I've been framing everything in terms of the Milky Way, but for example, in this homework problem, you're going to calculate. Well, as input you need the j factor for Segway, this dwarf galaxy, and it's just another galaxy. It's some distance away, and it's some mass, and it has some scale radius, and so it's going to be some number, which isn't going to be the same as another galaxy. And let me just say, actually, speaking of Segway, when you dig into the literature, you'll often find the j factors with the integral d omega here. So different people put the d omegas in different places. So sometimes this is dr rho squared of r, and sometimes it's defined as dr d omega rho squared of r. I don't like that definition because then you have to talk about what angular size you're looking at. But for people who mostly focus on extragalactic dark matter annihilation or in other galaxies, that kind of makes sense because you typically want to ask what's j within the region that I'm looking at. Whereas when you're talking about the Milky Way, since it's all kind of continuous, I think that this is a bit of a more convenient definition. But it's just a factor of where you put that d omega. But keep this in mind in case you look up a j factor and it's like 4 orders of magnitude different than what you think. Maybe it's just they put their d omega in a different place. Yeah?
Do you personally have a dark matter density profile you're partial to for the Milky Way?
Yeah, good. So I mean that's what we were talking about last time. And when you're far away from the galactic center, it's pretty clear that it's going to be something like an NFW. You can argue about the local dark matter density, which makes a difference because we square it. But when you get closer to the galactic center, then you have to think about in-body simulations with baryons. Ask questions like, is there a core? Is there a cusp? And that's where it becomes messier. And that's just like the cutting edge is it's messy. And so you need to look at those papers, see what people are finding in in-body simulations. Because also the potential is dominated by baryons in the inner few kiloparsec. So it's not like you can rely on data very easily to constrain the dark matter density because everything is dominated by baryons. So yeah, I have no good answer. I have no good answer to you. It's just you have to try different things, and you have to try to be conservative when you're setting limits. But keep in mind also for discovery that things might be more optimistic than you're assuming. Also, yeah. Okay, so I have like 5 minutes. I think maybe. Do I have 5 minutes? Actually, I don't know how much time. 3 minutes. Okay. So let me just mention. Let me start where we're going next time, and then we'll stop. So what I want to do now, given this story, and I'm going to kind of lay this out so that you can maybe think about it before tomorrow, or you can keep it in mind for tomorrow, is that we can look for this process with telescopes like Fermi. And so what I want to do next lecture, I'll just set up this problem for you today, is to estimate, without really thinking too hard, just kind of putting in numbers, what sensitivity the Fermi Gamma Ray Telescope should have to dark matter annihilation. And I'm just going to simplify things and assume the dark matter just annihilates into photons. So let me assume that I have dark matter, which can go directly into photons. And so this process has sigma v of about 3 × 10⁻26 centimeters cubed per second. As we went over for Higgs Xeno, this is not actually the case. And for most dark matter models, the gamma line is, is loop suppressed. But I just want to start here, and then we'll talk about the continuum cases, just because it's a little bit easier, because now dn gamma dE gamma, this is equal to 2 times delta of E gamma minus the mass of the dark matter, because you produce 2 photons per annihilation. So that part, at least, is easy, and we don't have to think about it. Then once we understand this, then we'll add in the continuum. OK, so let me just tell you what Fermi is in words, and then we'll stop. Fermi is a gamma-ray telescope, which was launched up into space in 2008, and it's been collecting data ever since. It is roughly a meter squared. Why? Because it has to be launched into space. And so that's about the size of things that you can easily launch into space. If you imagine launching something which was 10 meters squared, just think about a normal rocket that you see. That would be hard. So that just sets the d omega. dt, well, it's been in space since 2008. That's what it is. It looks at the full sky, a good fraction of the sky, about 20% or so of the sky at once. So that gives you some sense of d omega. And then another factor that you need to know is the energy resolution and the angular resolution of this detector. We'll over that a little bit next time, and we'll also talk about how this detector works, how do you actually observe gamma rays, and then we're just going to put in the numbers and estimate the sensitivity that you have to dark matter annihilation with Fermi. And then the punchline is, it's not quite going to be there for Higgs-Xeno dark matter. So the next time I'll mention a different set of telescopes, one in particular, CTA, the Cherenkov Telescope Array, which is going to be coming online in the next few years, which will have sensitivity to Higgs-Xeno dark matter. Cool. Any other questions? Awesome. One last thing. I haven't met most of you still. So if I haven't, I'd like to meet every single one of you. So introduce yourself like at the barbecue or something. I'd just like to meet you guys. Thanks. Yeah.
My name's Max.
Hey.
I just had a couple questions.
Yeah.
So you had this 1/2 flying around.
Yeah.
And I think you mentioned for indistinguishable particles you'd have
Yes.
1/2, but isn't it for distinguishable? Like if I
Oh, good. So what I mean is if dark matter annihilates with itself.
if dark matter annihilates with itself, I would expect no 1/2.
If you have the 1/2, because otherwise you're overcounting. Because what you care about is, like if I'm a dark matter particle, I want an n for all of the other dark matter particles. So, and then I myself at an m, so that's an n squared. But from the perspective of all the other dark matter particles, you're just another one of the things it can annihilate with. Okay. So if you think about that, then you realize you're actually double counting.
So then, okay. So but then if I have a partner then.
Yeah.
So now like if I think E plus E minus.
Yes. Then it's a different symmetry factor, because now n is divided by 2 before you square it, because you can only annihilate with half of the things out there. Exactly. But then you don't have that 1/2. So actually that's down by an extra factor of 1/2.
Okay, this is what I expect.
Yeah,
okay.
yeah,
okay,
yeah.
This makes sense.
Yeah.
I had one other thing I was thinking about.
Yeah.
So I guess, Fermi looked at like Andromeda and the Galactic Center,
Yeah.
Galactic Center, of course. But I guess I'm thinking, like, if you look at galaxies that are farther away, and if you assume that dark matter annihilation is happening, presumably they would have more in the past than the Galactic Center does today. So.
Oh, because they're at higher redshift, or?
Yeah, just because if the Galactic Center has been annihilating all
Yeah,
this time,
yeah.
and in the past there would be more, right? So I would expect.
Yeah, good. So extragalactic annihilation is another way of looking for dark matter annihilation, including going back to higher redshifts.
Sure.
It turns out the peak sensitivity is towards lower redshifts.
Is there a sweet spot?
Not really. It kind of just like is the lower redshift side, but with some slope. Okay. This actually worked out in a paper of mine. It has to do essentially with like how galaxies form as a function of redshift, and they do become denser over time, which is part of the reason. And there's a 1/r² flux factor. So when you convolve all of these things together, it turns out that the lower redshift galaxies are better.
I see.
But they're comparable sensitivity to local galaxies. The Galactic Center is still better.
I see.
The Galactic Center is the brightest thing on the sky by far.
Of course.
Because it's just so close.
Okay. And I'm sure people do this in like galactic clusters, not just looking at a particular galaxy.
Yeah. So I had a paper actually on clusters. I mean, that's the appropriate way to be thinking about it.
Yeah, because then
in clusters.
Then you kind of make this R-squared cancellation. I guess if you're looking at a small enough.
That's
angle,
right.
right.
That's right. Yeah. But still, the Milky Way is right there, and that just wins. Yeah.
Okay,
So if it's instructive to like plot everything on the sky. And if you plot it without a log scale, all you see is the galactic center. It's just, that's it. Yeah.
Excellent. Thank you very much.
Yep.
Hey.
Hey.
So you were talking about Susie being in trouble.
Yeah.
And I think you made a statement that it's more likely, or something along the lines of, it's more likely for the universe to be fine-tuned than it is that we miss something.
Oh, yeah. I mean, that's just my prior. Yeah.
So I'm just curious, like, where is that coming from?
Yeah. Because, for the past, 2 decades, we've been trying to think of that other thing.
Right.
And 2 decades ago, it seemed like, we were probably missing something. Probably there is another natural solution out there. We're not clever enough to think about it.
Right.
But I think what we've learned from these exercises is that it's really hard to construct natural solutions to the hierarchy problem with no new physics near the electroweak scale. Because you're trying to solve a problem at the electroweak scale. And all of the new physics somehow ends up coming out. I mean, it's typically near the electroweak scale.
Right.
Or you're working so hard to hide it that the model is just so convoluted that you can't, you have trouble believing even that it could be realized in nature.
Sure.
So that's plus the cosmological constant problem, which is there, which we have absolutely no idea what's causing. And
But that could be completely separate, right?
it could be completely separate, but it's not very reassuring that we haven't thought of any dynamical solutions to it. And those two things, and they both could be solved by some sort of anthropic reasoning. And they both seem to be kind of at the edge of criticality. So the anthropic solution just works.
Right.
And the dynamical ones don't seem to.
Anthropic solution being, if humans were to exist and able to think about these problems,
That's
the
right.
universe must exist in some way.
Yeah. But I would love for this to be wrong because, anthropics is horrible because you have no new physics.
Right.
Even though, conceptually, maybe it's the most interesting possibility, in the terms of finding new particles. It's not, except in the case of split SUSY, which I think is, essentially the philosophy is, if nature had supersymmetry as an ingredient, then wouldn't the multiverse select the supersymmetric vacuum because it's easier for it to select that vacuum? And that is a part of the other reasoning behind split SUSY, is in this multiverse, there would probably be some amount of supersymmetry because there's going to be more vacua with supersymmetric more supersymmetric vacua, which look like our own universe than non-supersymmetric vacua, if that makes sense.
Gotcha.
Yeah.
Thank
Yeah.
Hey,
Hey.
I don't know if this is a trivial question, but
Yeah.
the idea of annihilation of dark matter just looks a little bit weird to me, because when we find this estimate this cross section, we assume that when the dark matter fills out, it's just there.
Yeah.
But now we assume that this annihilation happens all the time.
Yeah.
So in principle, this could modify the original regular abundance we have when we make the assumption that dark matter doesn't annihilate.
Oh, but we do assume it annihilates. We assume it's been annihilating. That was